Good morning, everybody. I just want to welcome everyone to the seminar, right? It's part of the ECE Distinguished Lecture Series. It's my distinct pleasure to introduce today's speaker, Professor Shanhui. He's a professor of electrical engineering and applied physics at Stanford. Professor Fan is a senior fellow of the Precourt Institute for Energy and the director of the Edward L. Ginston Laboratory there. Professor Fan received his Ph.D. in 1997 in condensed matter physics from MIT. His research interests include the study of solid-state and photonic structures and devices with an emphasis on photonic crystals, osmotics, metamaterials. So he's published over 500 journal papers, has given over 300 plenary keynote invited talks, and has 62 patents. So Professor Fan has received numerous awards. I'll just name a few here. The David Lucille Packard Fellowship in Science and Engineering, the National Academy of Sciences W.O. Baker Award for Initiative in Research, and the Adolf Long Medal of the OSA, and also a Vannevar Bush Faculty Fellowship. This is the kind of highest distinction from the Department of Defense 3 years ago. He's a fellow of the IEEE, the American Physical Society, and the Optical Society of America, as well as SPIE. So today, Professor Fan's talk is entitled Control of Electromagnetic Fields for Energy Applications. Please join me in welcoming him here to Michigan.
Okay, well, thank you for the introduction and for inviting me here. It's really a pleasure for me to be here and to see many of my friends here. So I'd like to talk about control of electromagnetic field for energy applications. As maybe a brief introduction to my group, this is what we do for a living. So my group actually spends almost all our time solving Maxwell equations. So we're mostly a theory and computational group, and occasionally we do experiments. And in fact, most of the results I'm going to show are experimental results. But in the case of energy application, the reason that solving these Maxwell equations are important is because electromagnetics is actually very important in the context of energy. So I'll just give two examples. The sun, which is our primary source of energy, the energy comes to us through electromagnetic wave or optical wave at very high frequencies. These are on the order of a few hundred terahertz. On the other end of the spectrum, the way we got our access to energy, for example, you plug your computer into an outlet. Oh, can I use a pointer?
There should be one on it.
Yeah, no, I think this one works.
I'll run upstairs.
Okay, yeah. The other example is the access to the energy, and there you plug into a wall, and in fact, again, you're using electromagnetic field. These are at very low frequencies on the order of tens of hertz. So in spite of the fact that the frequency scale here, and therefore the usual impression of these fields are very different, the frequency here differ by 13 order of magnitude, the underlying equations are the same. And therefore advances that, or new ideas that one have in one area, for example in optics, can have very significant influence on other areas of electromagnetic spectrum as well. So with that as a background, here's a brief outline of my talk. I would like to talk on two areas. The first area are related to control of thermal radiation and radiative cooling. And these are on the relative high frequency end of the spectrum, where in this case we're thinking about the visible and infrared wavelength range. And then at the very end, I'm going to talk about some of our work in dynamic wireless power transfer. And these are the low end of the spectrum on the order of megahertz as well. So the first part of my talk is related to the control of thermal radiation. And again, as an introduction, this is a familiar picture when you think about thermal radiation. You heat something up and it radiates. So the most familiar example is the tungsten light bulb. And this picture of a light bulb, in fact, tells you quite a bit about blackbody radiation. You can see that the radiation is white. And that gives the impression that typical thermal radiation, for example, is very broadband. On the other hand, in the past 10, 20 years or so, there have been a lot of interest in thinking about thermal radiators with radiation spectrums that are very different. So this is an example that I take from Willie Padilla's group. What they did is they make these gold nano antennas. So what you see here are gold crosses with a size of a few hundred nanometers. And for these structures, what you can see is that its emissivity spectrum, it has very sharp peaks. They are not broad-banded at all. And so this actually gives you a possibility to significantly tailor their thermal radiative properties by controlling structures. And there are many possible applications in controlling the thermal radiation. And in this talk, I'm going to focus on just one. This is something that has occupied our interest in the past few years, and that is to harvest the coldness of the universe. So as you know, universe is very cold. The typical temperature scale is about 3 Kelvin. And from an energy or basic thermodynamics point of view, something that is cold is important. The fundamental Carnot efficiency limit says that if you want to convert heat to work or to electricity, you would like to have a high temperature heat source. The sun at 6,000 Kelvin, of course, is one of these heat sources. That's fantastic. On the other hand, you will also like to have a low temperature heat sink. Now, the vast majority of the energy conversion process that we use today use the Earth itself as a heat sink at a temperature roughly of 300 Kelvin. On the other hand, if you look up in the sky, in fact, you see a much better heat sink at a temperature of 3 Kelvin. So if you have a way to utilize this heat sink efficiently, you actually may open pathways to systematically improve vast amount of energy conversion efficient processes that are going on Earth. And the radiation part comes in because we do have radiative access to the outer space. The black curve here is the transmission spectrum of a typical atmosphere. And the important thing is that the atmosphere is typically transparent in the wavelength range of 8 to 13 microns. And that wavelength range happened to be the peak of blackbody radiation at the typical temperature around 300 Kelvin, which is not too far from our own body temperature. So the implication of this is that every one of us, in fact, if you walk out of this room, you will be radiating your heat out through the atmosphere to the universe. And therefore, you are actually doing cooling, or the process of radiative cooling. This idea has been recognized for a long time, and there has been a lot of work that goes in something called the nighttime radiative cooling. So if you have a black emitter, and you put it on the roof and have it radiate in the sky. Thank you. And you have it radiate to the sky. Then in this case, there's a heat dissipation process. So if you have the right thermal insulation, its temperature can fall below the ambient air temperature. In fact, it's not a hard experiment to show that you can readily get a temperature that's about 10 to 15 degrees Celsius below ambient. And this is a technology that people do use. One of the buildings at Stanford actually used this to produce some cold water at night. But it has not been a well-used technology for many reasons, but one of the simple points is that if you actually care about cooling or air conditioning, you probably would like to do it when things are hot, and things are usually hotter during the day rather than at night. So it certainly would be interesting to try to do these kind of radiative cooling process during the day as well. In spite of what I have told you about radiative cooling, if you take something black, go up to the roof at noon, and with the hope to see any radiative cooling, you won't see anything. In fact, because of the presence of sunlight, most of the things that you put under the sun will get heated up. So therefore, from there, the observation of daytime radiative cooling and what you need to do should be relatively straightforward. What you would like to do to get daytime radiative cooling is to create a system which has very strong emissivity in the 8 to 13 microns so that the heat can go out. But in the meantime, it doesn't absorb any sunlight. So you want to build a mirror in the entire wavelength range of the sunlight, and that goes from visible to near infrared. And so once you realize that's what you need to do, then coming from a theory background, it's not too hard to imagine that you can design a structure that can go about doing this. So this is our first attempt we use some of the idea from photonic crystal and nanophotonics to come up with a structure that has a spectrum that may resemble something that looks like this. And we did a theoretical calculation to show a few things that, in fact, if you've done this right, this kind of structure can get to a temperature that's below the freezing point of water, even under direct sunlight, and in a way that's entirely passive. And also, you will have a cooling power density exceeding 100 watt per meter square. So these are the theoretical calculations that we did in 2013. It's not going to be obvious in this talk, but we are actually a theory group, so this is most of the work that we do. But in this case, when we look at the theoretical calculation that we have done, what we have concluded was that this is in fact simple enough that we could actually go about doing an experiment to demonstrate it. So this is the experimental demonstration. So this is done by Ashwas Raman, who is now the professor at UCLA, and Lin Xiaozhu, who is sitting there, who is now a postdoc in Professor Reddy's group here in Michigan. So in the experiment, what we did is we got a wafer on silicon and with a silver mirror. And on top of the silver, we put 7 layers of dielectric made of silica and hafnium oxide. Silicon dioxide, they are silicon atoms and oxygen atom, and they vibrate against each other, and that produce thermal radiation with wavelength that peak around 10 micron. So it's exactly what we would need for radiative cooling purposes. And some of these layers are put in also to push the reflection edge of the silver mirror further towards ultraviolet so that the system actually has strong solar reflection. The average solar reflection over the entire spectrum exceeds 95%, which is what you would need in order to see radiative cooling. And on the thermal side, you see an emission peak. So when we put this thing on a roof, and this is the roof of our electrical engineering building, the black curve is the ambient air temperature. The green curve here is the measured solar irradiance directly on top of our sample. And the blue curve here is the measured temperature. So what you see here is that even under direct sunlight of having 900 watt per meter square of sunlight directly hitting the sample, the structure actually has a temperature that's about 5 degrees Celsius below the ambient air temperature without any electricity input. So this is in fact the first demonstration of anything that you put under the sunlight that it would spontaneously lower its temperature rather than increase its temperature. And the structure has a temperature that's below the ambient air, and therefore you could heat it up to heat it back to ambient air temperature. And the amount of heat that you need to put in to heat it back up into the ambient air temperature give you a measure of the cooling power density of the system. So in the experiment, we put a thermoelectric cooler in the back and heat it up. And it takes about 40 watt per meter square of cooling power to heat it back to the ambient air temperature. And that gives a sense of the kind of cooling power density that we see in the experiment. Theoretically, and people now have demonstrated, this cooling power density can exceed 100 watt per meter square. So this is our own first experiment, and it took a few years before other people start to realize that this is not too hard an experiment to do. And so by now there has been a very large number of experiments that has been carried out over a very wide variety of structures and materials that can achieve daytime radiative cooling. This includes, in fact, some study on biological creatures such as ants, as well as these days going into very large-scale production of thin film systems that can do daytime radiative cooling. One of the questions that naturally come up from this is, well, how do one actually use this in practice? So the natural way to think about these radiative cooling structure is to use it for building air conditioning. Modern buildings, however, are very well insulated by design. And so doing cooling on roof, which is what daytime radiated cooling needs to be because you need sky access, by itself would not directly influence the thermal footprint of a typical modern building by much. So in order to use this for building cooling purposes, therefore one need to be able to deliver the coldness into the building. And there already exists systems to do that, and that's your standard air conditioning system. So the natural question is to be able to couple the daytime radiated cooling system into a standard air conditioning system. So here is one of the subsequent experiments that we have done. We have also our own large-scale sample on the order of a few meters squared, and we made them into panels. And underneath the radiated cooling panel, we put a water pipe, a circulating water pipe, so that we can cool the temperature of running water to a temperature that's about a few degrees Celsius below ambient. And then you can use that water to drive the standard water-based cooling tower. And a system analysis would indicate that if you can cool the water inlet temperature by about a few degrees Celsius below ambient, you can improve the air conditioning system efficiency by about 10 to 15%. And 15% of the US power consumption goes to air conditioning. And in hotter countries, this number is even larger. So we think that this may actually open up the opportunity to significantly improve the efficiency and lower the power consumption for air conditioning system. So with two of my former postdocs, we started a company called SkyCool System in really trying to push towards commercial deployment of these kind of technology. From a more fundamental point of view, on the other hand, one of the questions that one may ask is how cold can you get in these systems? The initial experiment that we have done give you about a 5 degrees Celsius reduction from the ambient air. Now, as a theorist, you can ask exactly what the theoretical limit might be. Well, given the fact that the outer space has a temperature of 3 Kelvin, and what we're trying to do here is really try to establish a thermal equilibrium to the outer space. You ideally would think that one should be able to get 3 Kelvin out of it. And more specifically, imagine that you have an idealized atmosphere which has 100% transmission over a particular wavelength range. And if you design a thermal emitter that only have emissivity in that range, then you should be able to get 3 Kelvin. Now, most of the atmosphere are not that good. The blue curve here is the transmission spectrum at Stanford. And it's a very good atmosphere. It has a transmissivity of about 90%. Using this, if you imagine a selective emitter with the emissivity spectrum indicated by the red line, and you do the theoretical calculation, you get rid of all the parasitic heat load, one should get a temperature that's about 40 to 60 degrees Celsius below the ambient air temperature. And this, in fact, is what we predicted in our initial paper on daytime radiated cooling. To do that, you will need to get rid of all parasitic heat load. And so what we do experimentally is we constructed a vacuum chamber, and then we put the radiated cooler inside the vacuum chamber. And with the vacuum chamber, we can cut off all the convective and conductive heat loss. And in the experiment, we get a temperature reduction from the ambient. That's about 40 degrees Celsius. And this is an experiment that runs over a period of 36 hours, so it actually goes both day and night. There are a number of interesting things about this experiment. One of them is, in fact, you can see that the temperature reduction from the ambient is largest during the daytime. And if you think about it, this may actually make sense because this is an object that's trying to pin its temperature to outer space. And it really, if you do the thermal insulation right, should not care about the ambient air temperature. So therefore, the higher the ambient air temperature, the higher the temperature reduction. So that's at least one of the interesting features about this. This is a temperature that's at the ambient temperature around 10 degrees Celsius or so, is way below the freezing point of water. And that point to some of the interesting possibility for passive storage for food or medicine below the freezing point of water, and that's something that we're pursuing as well. So, starting from the concept of radiative cooling, one could in fact combine that in some way with solar energy utilization. And the realization here is that radiative cooling is using the mid-infrared wavelength range of 8 to 13 micron, whereas the solar wavelength range is in the visible or near infrared. So consequently, one could simultaneously harvest the sunlight as well as to do radiative cooling using the same real estate. And here is one demonstration where we take the same vacuum chamber and where contains the radiator cooler, but we put on top of it an infrared transparent solar absorber. So in this case, experimentally what we do is we put in a germanium wafer. And the sunlight will be absorbed by the infrared transparent solar absorber to heat up the solar absorber, and therefore one can harvest the sunlight for heating purposes. In the meantime, the thermal radiation coming out of the radiator cooler will still go through the solar absorber to the outer space, and therefore one can still do radiative cooling. And so this is the experimental demonstration where we heat up the solar absorber above the ambient air temperature simultaneously with a radiative cooler temperature that's still substantially below the ambient air temperature. From a practical point of view, given that the rooftop real estate is limited, what this points to is the possibility of integrating radiative cooler with solar energy harvesting. And also, from a fundamental point of view, this in fact allow you to rethink about some of the fundamental thermodynamic limit of solar energy harvesting. When you typically think about your solar cell, you think about a solar cell that's using the Earth as a heat sink. And that translates into a sequence of solar cell efficiency limit. On the other hand, if instead you imagine a solar harvesting, energy harvesting system where you use not the Earth but the outer space as a heat sink, you could actually overcome all these fundamental thermodynamic limits. And that's something I think that's actually quite intriguing in thinking about how really one can use this for solar cell design. From a slightly more practical point of view, most of the time when we use about solar energy, we're not using a solar cell. Rather, for example, if I see you outside, I'm actually using sunlight reflected from you to do object identification. So, so in fact, much of what we think about the visual appearance of an object come from the absorption and reflection properties of sunlight. On the other hand, in addition to visual appearance, you would like also to be able to control the heat load of an object. Certainly, depending on the weather, you may be interested in either enhance the possible heat load for heating purposes or reduce them for possible cooling purposes. In other words, you would like to be able to keep the visual appearance of an object the same while having the capability of controlling its overall heat load. So with that, it would be useful to talk a bit about the radiative thermal load of a color object. So the color object, of course, the color comes from the response of an object to the visible spectrum. In fact, there is an effect called metamerism, which basically says that human eyes are not really spectrometer. In fact, different visible spectral response, very different visual spectrum response, can give rise to identical color response. And so you could actually manipulate solar absorption of an object using this effect. In addition to the visible side, you have the infrared solar absorption. Depending on whether you absorb that sunlight or not, you can control the heat load of an object, as well as the radiative cooling on the mid-infrared side. So using this idea, you could actually control the radiative heat load of an object under the sun over a very large range by keeping the color the same. So here is a numerical demonstration. We have two yellow objects, and in the cold object, we designed it to absorb as little sunlight as possible, but to do strong radiative cooling. And in the hot object, we do the opposite. We design it to have a very strong absorption of sunlight and to shut off radiative cooling. And you can compare the radiative heat load of these two objects, and they differ by more than 800 watt per meter square. To put this in context, a typical sunlight radiation is about 1 kilowatt per meter square. So this is an enormous variation of the range of heat load that you can do. And that then translates into very substantial temperature variation of these objects under sunlight. So as a demonstration, we make two structures. These are all multi-layer structures based on the prescription that I was talking about. Both of these structures are pink-looking objects, but they are designed to have maximally different thermal response in terms of absorption and radiative cooling. And so again, we do our rooftop experiment. Under sunlight, the temperature of these two objects actually differ by about 50 degrees Celsius. And the commercial paint that's also pink has a temperature that's somewhere in between. And that basically tells you the range of temperature response that you can get. And also, somewhat interestingly, this object actually has a temperature, the hot object here has a temperature that's about 10 degrees Celsius above a commercial black paint. So this, I think, point to really the possibility of influencing the thermal load of color object for buildings and for automobiles and so on to control its cooling and heating response. So up to this point, I focused mostly on radiative cooling during the daytime. And in those cases, one need to combine mid-infrared radiation control with the control of visible spectrum. In the third part of my talk,
You don't get it. Students has all these questions, you know.
The first question.
answer it later. Okay, so in the third part of my talk, I'm going to switch back into nighttime radiative cooling and talk about some of our effort in nighttime power generation. So up to this point, we're using the universe itself directly as a heat sink. On the other hand, from basic thermodynamics, anytime that you have a heat flow between two reservoirs with two different temperatures, in other words, you have a non-equilibrium situation, you should be able to harvest that heat flow to generate work. So here you have a temperature gradient of 300 Kelvin Earth to 3 Kelvin universe. And also, you may ask, how much energy are there in this particular heat flow from the Earth to the outer space? Well, the Earth, roughly speaking, is at thermal equilibrium. The temperature of Earth doesn't change by too much. And so that must indicate the amount of solar radiation that's come in has to be balanced out for the amount of outgoing thermal radiation. So in fact, in outgoing thermal radiation, you will have the amount of power that you can harvest that in terms of order of magnitude that's comparable to incoming solar radiation. And that's an enormous resource. And in this case, it is somewhat surprising that most of the renewable energy research at the moment have focused on harvesting the heat flow from sun to the Earth. And what I would like to argue is there is a possibility to look at the complementary process as well. So since we already have a radiative cooler at night, and this is just a black object facing the sky, and that has a temperature below the ambient, one could simply take a radiative cooler and couple that to the ambient through a thermoelectric generator to generate electricity. And this is not a complicated experiment. This is our part of the experimental setup that we do. What you see here, the top here is simply a black thermal radiator, and then the thermoelectric module is underneath it. And with this, experimentally, we can observe a power density of 25 milliwatt per meter squared. And if you further optimize the system in detail, we think one can get to about half a watt per meter squared out of the system. Now, this doesn't look much. A typical solar cell gives you a couple hundred watt per meter squared. But this operates when the sun is not shining. And in terms of application, this amount of power density is sufficient to light up a light-emitting diode. And in this case, we are actually generating light from the darkness of the sky. About a billion people in the world actually lacks access to electricity at night. And so developing a low-cost module that is stable, that can directly generate light at night, can have a potential, really have a large potential impact. And that's something that we're actually quite excited about. And in this case, this provided direct nighttime lighting without the need for electricity storage. So this is a relatively simple experiment. From a fundamental point of view, there are in fact other interesting physical processes that one can use to try to extract electric power from the darkness of the sky. And as one of those, it turned out that the same optoelectronic physics of photovoltaic cell that one used to harvest sunlight can also be directly used to harvest the darkness of the sky. So in the case of a usual photovoltaic operation of a cell, you will have a cell facing an object such as the sun that has a temperature above the cell. In this case, there's a net photon flux coming from the sun into the cell, and that generates electric current. So this is the typical photovoltaic operation of a solar cell. Now, it turned out, if you look at the theoretical derivation for the cell, you will realize that if instead you have the same photodiode, but instead of facing the sky, instead of facing the sun, you have it face the sky that has a temperature that's below the temperature of the cell. So in this case, there's no photon coming in, but there's a net photon flux going out. And it turned out that when you have a net photon flux going out, therefore you have an absence of photon coming in, you also produce electricity on the diode. So you could in fact use the same physics that you do for solar energy harvesting to harvest the coldness of the universe. And let me give you a more detailed microscopic argument on where this energy coming from. So if you look at a p-n junction physics, in equilibrium, when the source has the same temperature of the cell, then you have the generation and recombination current that balances each other. When the cell is facing a heat source that has a temperature higher than the cell, the generation current dominates over the recombination current, and therefore you can send external current to the outside to drive a load. Similarly, if the heat source has a temperature below the cell temperature, then in this case, the recombination current is going to dominate over the generation current. And again, there will be excess current that you can use to drive the external load. So in terms of a IV curve here, the standard diode at equilibrium has an IV curve that's indicated by the black curve here, which passed through the origin of the IV plane. In the typical photovoltaic cell, in the presence of external radiation, the curve shifts downward, and by operating in the fourth quadrant, one can generate power. On the other hand, in the negative illumination mode, one moves the curve upward, operate in the second quadrant, and again to give you power generation. This analysis is in fact implied in the standard Shockley-Queisser analysis, but remarkably has never been explicitly demonstrated experimentally. So we therefore did this experiment where we take a MCT optical diode, we have a phasor emissive surface where we can control its temperature to be either above or below the ambient air temperature. And for signal processing purposes, we have an optical chopper in between with rotating blade that periodically block the optical access between the emissive surface and optical diode. So as the chopper rotates, therefore, you would expect that the current of the diode to fluctuate. And this is, for example, you would expect the current go up and down as the chopper rotates. Now, one thing, if you go back to the IV curve, is that as you move from the fourth to the second quadrant of the IV curve, the current changes sign. So depending on the temperature of the emitter to be either above or below the diode, you would expect to see a 180-degree phase change in the current fluctuation as the chopper rotates. And that's exactly what we see in the experimental setup, and that gives a direct indication that one can produce these kind of photocurrent from negative illumination. And more recently, we have actually taken the setup and go to our roof to do the experiment for a direct power generation from the sky as well. Now, up to this point, I've shown you the possibility of getting power out of the sky directly. The amount of power that we see is relatively small. And so from a theory point of view, it would be interesting to ask, what exactly is the theoretical limit for harvesting these kind of outgoing thermal radiation? And in the solar energy harvesting, there has been enormous amount of work trying to work out the fundamental thermodynamic efficiency limit for a wide variety of scenarios. And these typically involve putting some sort of a heat engine on the cold side, which is the Earth, and try to work out what the limits are for energy conversion. And as it turned out, you could take this entire body of theoretical work and map them into the theoretical limit for the capability of harvesting outgoing thermal radiation. In this case, you will have a heat engine on the hot side and to convert the outgoing radiation into work. And you can work out the thermodynamic limit. So every one of the standard limits of solar energy harvesting, in fact, has a corresponding limit for power density limit on harvesting outgoing thermal radiation. And if you do this calculation, what you realize is that the typical number that's coming out of the outgoing thermal radiation between the 300 Kelvin and the 3 Kelvin reservoir with the heat engine sitting on the hot side is on the order of maybe approximately 50 watt per meter square for reciprocal systems, increasing to more than 100 watt per meter square for non-reciprocal systems. The number that I'm quoting you experimentally, which is our own number, is about maybe on the order of 25 milliwatt per meter square, and about 4 order of magnitude below this. So given that we never think of ourselves as the best experimental groups in the world, I think I like to interpret this discrepancy as a really tremendous amount of opportunities that one really should think about in better improving the experimental technique to harvest the outgoing thermal radiation. So I think this concludes the major part of my talk, where we are talking about really harvesting sunlight, trying to control mid-infrared radiation that is at the high frequency end of the electromagnetic spectrum. in the final maybe 10 minutes or so, I like to go down to the low frequency end, where we use electromagnetic field to provide access to these energy. And in particular, I'm going to talk about wireless power transfer. So this is a subject, of course, that has a long history in electromagnetic research. I'm at the moment plugging my laptop directly into the power source. It certainly will be interesting to try to cut the cord in order, but also have access to power. And there are many ways to do so, because electromagnetic naturally is a wireless, electromagnetic field naturally is a wireless transfer of things. So there are many ways you can do it. For example, you can have a direct transmitter sending a microwave or a laser to a receiver to send power. This allows you to do long distance power transfer. In fact, the way we use sunlight also belongs to this category. So it's really long distance power transfer. But it requires line of sight. If you do not like to have this line of sight issue, you can do inductive transfer, where you have two coils, where the magnetic field of one of the coil will drive the current in the other coil, and that will give you a power transfer as well. And you do that, for example, in a number of electric toothbrushes or cell phones and so on. Now, in this case, the transfer distance is actually very limited. This is way below centimeter. And there's a way to enhance the distance of the inductive transfer. And this is by couple two resonators together. So you add a capacitor on each side of the inductor. And as you do that, you have two resonators, and they resonantly couple, and you can send power from one to the other. And the power transfer in this case is through the coupling of the magnetic field. This is a very old idea. Apparently Tesla has a patent about this. In 2007, there is a very nice experiment coming out of MIT that really point to some of the very interesting aspects of this wireless power transfer scheme. So this is a group from Marin Soljacek and John Janopoulos. They were all sitting there, and they were sitting between two coils over a distance of a meter. And you can see a light bulb on this side actually lights up. This, I think, is a very nice picture, because there's no line of sight. They were directly placing themselves to block it. Also, typically, I think their light bulb is on the order of tens of watts. Usually, you wouldn't like to have that amount of electricity pass your body. On the other hand, obviously, the pointing vector for sure points through these guys' body. And I happen to know these people very well, so this is 12 years ago, and they still roughly look like this. So there's something good to say about it. Okay? So this is really an experiment that has generated a lot of interest in this particular class of wireless power transfer scheme, and in fact has been commercialized. However, there is in fact an intrinsic problem about this kind of wireless power transfer scheme, and that's related to the robustness of the system. So you could in fact write down a couple mode theory model, which is basically just two resonators, and the transfer efficiency in fact is just the transmission coefficient. When you inject power from the left, how much of it transfers to the side, to the right. And if you plot the transfer efficiency spectrum, because you have two resonators, and if they're strongly coupled together, then you have two peaks. And at the peak frequency, the transfer efficiency reaches 100%. So you could actually get high efficiency transfer. But the problem with this is that as you vary the distance between these two resonators, then the coupling changes, and so the eigenmode frequency depends on the distance. So what you can see is that the peak frequency actually moves as the distance moves. And so if at every distance you change the source frequency and you plot out the efficiency, then you get a curve that looks like this, where the efficiency is very high at short distance, and that is flat. And then it decays when you go out of the strong coupling region. And this is the experiment that I have demonstrated. In fact, for every distance between the source and the coil, they readjust the circuits. On the other hand, if you don't readjust the circuit, for example, you fix the frequency, Now in this case, when you plot out efficiency, then in this case, you will get a curve that looks like this, that the efficiency peak only at a particular distance. And when they get closer, the efficiency actually drops. So the take-home message is that for this kind of scheme to work well, for every distance variation, you have to readjust the circuit. If your goal is to charge a stationary object, this is not a major issue. The thing is there, you can readjust it. On the other hand, there are scenarios where you would like to do dynamic charging. You would like to do wireless power transfer to a moving object. In this case, the transfer condition continuously changes. And therefore, if you want to apply that kind of scheme, you would need to continuously adjust the circuit. As a somewhat aspirational hope or example, you can imagine trying to do dynamic charging while a car is running on a highway. And in those cases, it is in fact extremely difficult to construct a circuit to be able to adaptively adjust to the changing condition. So with this in mind, what we set out to do is to come up with a scheme that doesn't suffer from this kind of limitation. And we would like to come up with a scheme where you can maintain transfer efficiency as the distance is varying without any external adjustment to the circuits. And this here, we borrow a concept from optics that has generated very substantial interest in recent years. This is the idea of a parity time symmetry. So this is a class of, on the optical side, a class of structure where you consider system with balanced gain and loss. So in our case, in using this concept, instead of a radio wave frequency source at a fixed frequency to drive the circuits, what we propose to do is to get rid of the radio wave frequency source and instead put an amplifier inside one of the source resonator. And the physics of parity time symmetry system, where people have extensively explored in optics, involve two resonators. One has gain and the other one has loss, and you fix the gain to be equal to the loss in magnitude. And in doing so, you can plot out the eigenfrequency of the system, and they have this bifurcation behavior where in the strong coupling regime, you have real frequency and they bifurcate. And in the weak coupling regime, the frequency coalesces but the imaginary part bifurcate. Now, what we do in our system is to take this prototypical system, but in addition, put in a gain that's physical. Now, the actual physical gain here has nonlinear saturation. So consequently, in this case, instead of talking about eigenstate, you can talk about oscillation frequency. And what you see here is that at strong coupling regime, you have a bifurcation of the oscillation frequency, and they coalesce when you move the coil far from each other in the weak coupling regime. And because these are steady state, the imaginary part frequency is always fixed. Now, so in this case, what you see is that the oscillation frequency changes as a function of distance. And also the oscillation frequency happen to be very, very close to the eigenfrequency of the system. And if I remember what we talked about in the wireless power transfer scheme, the highest efficiency occur at those frequencies, the eigenfrequency of the system. So this is a case where the system actually generates oscillation exactly at a frequency where high efficiency wireless power transfer occurs. So therefore, using this, one should be able to produce high efficiency wireless power transfer without any external tuning. So if you do theoretical calculation without any external tuning, the drag curve here is what a conventional scheme would look like. You have high efficiency only at a particular distance. The blue curve is our PT-symmetric scheme. Again, without external tuning, you will have a region where the efficiency is independent of the distance. And so here's the experimental setup. We have two coils, copper coils, The white thing here is the capacitor, so it's an LC circuit. And on the receiver side, we put a light emitting diode, as I'm going to show you, so that we can visually see how the wireless power transfer efficiency depends on the distance. And then on the source side, we either do the conventional scheme where we drive it with RF frequency source, or we do our PT-symmetric scheme where we put in the gain medium. So first, let's do the conventional scheme. As we have said, in the conventional scheme, you expect to see high efficiency only at a particular distance. So here is a movie. Sid, who is the graduate student who did the work, is going to just do the experiment.
What is the RF frequency here?
This is a few megahertz. So what you see here in this experiment is that the LED, as he's pushing it, the LED lights up, but only at a particular distance. And as you push the coil close to each other, the efficiency actually drops. The LED actually no longer lights up. Okay. So with this as a background, now we can demonstrate what we see in the PT-symmetric scheme. So in this case, what you would expect to see is while the coil is moving in this range, the LED will remain lighted. And so here's a Sid again. So you can see that the LED lights up right away. And as he pushes it, it remains roughly constant over a range until it's too far. And you can look at when he pushes it backward as well. And so this gives the indication that it is indeed possible to do robust dynamic wireless transfer while the receiving object is moving in these resonance schemes. So you could actually measure quantitatively the transfer efficiency and also correlate that with the oscillation frequency of the system, and the transfer efficiency indeed remains high in the strong coupling regime when the frequency bifurcates, and when the system goes through a PT phase transition, the efficiency drops. So the physics that we talked about indeed show up in the experiment. In this particular experiment, we have demonstrated a transfer efficiency that's near ideal. On the other hand, the overall efficiency of the system is the product of the amplifier efficiency and the transfer efficiency. So in the first experiment, we use something called a negative impedance amplifier, which does not have high amplifier efficiency. And as a result, the overall system efficiency is on the order of 30%. So in the more recent experiment, what we have done is to replace this with what's called a switch mode amplifier to push the overall system efficiency beyond 90%. So in the operation of a switch mode amplifier, it is known that these kind of amplifier can provide a much higher amplifier efficiency. However, the high amplifier efficiency occurs only when the external impedance load is at a particular value. So what is actually quite interesting in these PT-symmetric circuit is that at the operation point, the external load on the amplifier, because of this PT-symmetry condition, in fact does not depend on the distance as well. So that actually enables the use of these kind of high efficiency switch mode amplifier for near complete system efficiency in these systems. So with that, I think I should summarize. So what I hope to convey is that electromagnetics is actually very, very useful in energy application. There are really a lot that you can do simply because electromagnetic field is such a fundamental aspect of nature and is really ubiquitous in almost any energy conversion system that you can think of. And therefore, many of the recent development that people are thinking in optics or electromagnetics, many of them in fact can have very important implications in thinking about energy as well. So to end, let me acknowledge many of my former and current students and postdocs who have done this work over the years, and many of them have moved on to sunnier or better places. So with that, let me stop and thank you for your attention.